towering cities, the global network of machines, the sheer volume of material we move and synthesize, all of it is etching the Anthropocene into the geological record.
Right. It's marking this moment in time as the undisputed first age of human industry.
Exactly. And it's a compelling narrative, isn't it?
It is, that feeling of being the first, the inevitable culmination of planetary evolution.
Yeah.
It really anchors our history, our understanding of Earth's timeline.
It does, but that confidence, that certainty, it raises one of the most provocative and fundamentally difficult questions that science has grappled with recently.
Which is?
What if we're wrong? What if deep beneath our feet, preserved in the silence of deep time, there lies a faint echo of another industrial age?
A civilization that rose, industrialized, and then just vanished.
Vanished, erased by millions of years of geological churning.
That thought experiment is really the foundation of our deep dive today. It's called the Silurian hypothesis.
And we should be really clear here. This isn't about, finding ancient alien wreckage or debunking history.
Not at all. This deep dive is designed for you to grasp the core scientific mission that's proposed by this hypothesis. It treats a possible vanished industrial civilization not as a myth, but as a question of detectability.
Detectability in the geological record.
Exactly. Can you find it? And if you can't, why not?
Okay, so let's unpack this a bit. We're dealing with sources that explore the very limits of what geology can tell us about the distant past. They're setting up these challenging, really specific criteria for finding evidence that might predate modern humans by tens of millions of years.
Maybe even hundreds of millions.
Right. So our mission here for you is to understand the forensic methods, the tools required to locate a geological fingerprint that might only exist as, a faint smudge in deep time.
That's a great way to put it. And that mission has immediate value, even if we never find a shred of evidence for a Silurian civilization.
How so?
Because the very act of defining the search criteria, of figuring out what to look for, forces us to sharpen the tools we use to analyze our own impact on the planet, our own Anthropocene.
So it's a mirror.
It's the perfect mirror.
Okay, so what's the origin story of this whole idea? Where did it come from?
Well, the hypothesis was formally proposed back in 2018 by astrophysicist Adam Frank and climate scientist Gavin Schmidt.
And they weren't archaeologists or paleontologists?
No, and that's key. They weren't looking for ancient ruins. They were trying to define the planetary signature of industrialization in a completely time-independent way. What does industry look like from a planetary science perspective, no matter who or what is doing the industrializing?
And for anyone who loves a good historical nod, the name itself, the Silurian hypothesis, it's a fantastic piece of science fiction homage.
It really is. It references the fictional reptilian Silurians from the TV show Doctor Who.
Right, who were imagined to have built this high-tech civilization long, long before humanity ever showed up.
And that's the fun part. It connects that joy of speculation with the real rigor of planetary science. But the scientific focus is intensely serious.
How so?
It uses the known markers of our Anthropocene age, the chemical, the physical, the climate disruptions we are causing right now. And it asks a simple question.
Okay.
If those exact same markers showed up in the rock record from 60 million years ago, could we still recognize them as artificial?
Or would we just, file them away under natural climate anomalies?
Precisely. That's the core question. And that brings us right to the central challenge here. If we can't look for buildings or, written language, what specific indelible marks would a complex industrial civilization actually leave behind?
We need to understand the unique, persistent fingerprint of industry that could somehow survive the immense destructive power of geological recycling.
Right. We have to move beyond any idea of surface artifacts entirely. Forget finding a fossilized microchip.
So our focus has to shift.
It must shift to systemic changes. We're looking for evidence of massive, rapid shifts in global biogeochemical cycles that really only two things could cause.
Industry being one.
And an exceptionally rare and violent natural event being the other. The key characteristics we're looking for, the things that define an industrial civilization's mark, are speed, breadth, and artificiality.
Let's start with the chemistry then, because that feels like the most fundamental change. Our modern era has fundamentally altered the planet's baseline chemistry.
It really has.
And the clearest, most lasting signature we've discussed, it involves isotope anomalies, specifically with carbon.
Yes, the carbon isotope anomaly.
Yeah.
It's typically denoted in the science as delta C13, delta dollars, and it is arguably the most critical marker we could possibly look for.
Okay, so break that down for us. Why is it so important?
To understand why, you have to appreciate where fossil fuels actually come from. They're derived from ancient organic matter, right?
Plants, microorganisms, all that stuff.
Exactly.
Yeah.
All that life that converted atmospheric CO2 into biomass millions and millions of years ago.
And during photosynthesis, those organisms, they have a preference, right? A kind of kinetic fractionation preference.
That's the term, yeah. They find it easier to absorb the lighter isotope of carbon, which is carbon-12, rather than the slightly heavier, more sluggish carbon-13.
So they're picky eaters, chemically speaking.
They are. And this makes all that long-buried organic your oil, your coal, your natural gas significantly lighter or depleted in carbon-13 compared to the baseline CO2 that's just naturally in the atmosphere or dissolved in the ocean.
Okay, so that's the setup. What happens when a civilization comes along and starts burning trillions of tons of this ancient light carbon really, really fast?
Well, you cause a profound and, more importantly, a measurable global shift. The sudden massive input of that carbon-12 rich material, it dilutes the entire global carbon reservoir.
So the ratio changes.
The ratio of carbon-13 to carbon-12 drops sharply, everywhere, all at once. That depletion, that negative spike, is the absolute definition of the modern Anthropocene carbon signal.
How significant is this spike, really? And how does it get preserved for millions of years?
Oh, it's incredibly significant, mostly because of its rate and its magnitude. The speed is the key. And we measure this shift in all sorts of geological media, but most famously in deep-sea foraminifera shells.
Foraminifera?
Yeah, they're tiny little marine organisms. They build their shells from calcium carbonate, and in doing so, they lock in the ocean's isotopic signature at the very moment they lived and died.
So they're like tiny floating time capsules.
Perfect analogy. A rapid negative delta C13 excursion that's preserved in successive layers of these shells would be, the primary piece of evidence of a previous civilization burning long-buried organic fuels on a truly global scale.
That's the signature of the fuel source itself. But industrial activity doesn't just leave a carbon footprint, it inevitably causes a global thermal response, a fever, and that leads us to the temperature spikes, which are recorded by a different set of isotopes. Oxygen isotopes, or delta O18.
Right, and this is how we connect the carbon release to the effect on the climate. Delta O18, which is the ratio of oxygen 18 to oxygen 16, serves as a crucial proxy for temperature. We see it especially when we examine ice sheets and ancient carbonate sediments.
Okay, so explain that mechanism. How does temperature data get locked into a rock?
It's pretty elegant, actually. Water molecules that contain the heavier oxygen 18 evaporate less readily than the ones with the lighter oxygen 16.
Okay, that makes sense. Lighter things float up easier.
Exactly. So when the climate cools down and big ice sheets form, that lighter oxygen 16 gets preferentially locked up in the ice. This leaves the remaining ocean water enriched in the heavier oxygen 18.
And the little foraminifera build their shells out of that heavy water.
And that signal gets locked into their shells, into the marine sediments. Conversely, rapid warming, which is what a massive industrial carbon release would trigger, it would melt that ice, releasing all that light oxygen back into the ocean, changing the ratio again really fast.
So you'd see a recognizable inflection point in the delta O18 record across multiple sites around the globe.
A sharp, clear spike. And the key word there, as you said before, is rapid. We see natural climate cycles all the time. They happen over tens of thousands of years, driven by orbital mechanics, the Milankovitch cycles.
But an industrial civilization's impact, burning fuels over, a few centuries, that would cause a thermal event that is geologically instantaneous.
Instantaneous, a razor-thin line in the rock record.
Yeah.
So what we're looking for is a sharp spike in that delta O18 record that happens way faster than any known natural, astronomical, or geological cycle can account for.
So it's a combination.
It's the essential 1-2 punch of the industrial fingerprint. The rapid delta C13 drop, showing the fuel source, and the simultaneous rapid delta O18 spike, showing the climate impact.
Now let's move beyond just energy and climate. A huge part of any large, settled global population is, it's feeding itself.
Absolutely. Food production.
And our sources emphasize the disruption of another major cycle, the nitrogen cycle, which is measured through delta N15.
This is a really interesting one because this is where synthetic fertilizers become the crucial marker. Modern industrial agriculture is completely 100% reliant on artificially fixing atmospheric nitrogen.
Using the Haber-Bosch process.
The massive energy-intensive Haber-Bosch process, yeah, to create ammonia-based fertilizers.
And then that's very, very different chemically from how nitrogen is fixed naturally, right, by bacteria in the soil.
Oh, fundamentally different. And the isotope signal shows it plain as day. Natural processes, they tend to fractionate nitrogen isotopes in a particular way. But synthetic fixation and the subsequent massive runoff from farms, it creates a very distinctive and widespread isotopic shift.
So the whole global nitrogen cycle gets thrown out of whack.
It gets completely altered because the sheer volume of this artificial nitrogen just overwhelms the natural pathways. And this results in these distinct nitrogen isotope shifts, the delta N15 being embedded in ancient soils, in river delta sediments, and maybe even in certain persistent organic molecules.
So finding a widespread delta N15 anomaly would tell you something very specific. It would differentiate an advanced industrial society that depends on massive artificial food infrastructure from, say, a huge population of hunter-gatherers.
Or even pre-industrial farmers who are just relying on natural compost.
Yes, it's a marker for global, technologically supported logistics.
It really is. It acts as a marker for a technological choke point. The need to feed billions of individuals by actively manipulating planetary chemistry on a vast scale.
A Silurian society would have to do something equivalent.
They'd require an equivalent planetary manipulation, whether it's through their own version of Haber-Bosch or some other energy-intensive artificial means. And that manipulation, that will always leave a ghost signature in the rock.
Okay, so beyond these huge global cycle disruptions, the search also has to look for the physical stuff, the persistent residue, the pollutants and the materials that just refuse to degrade back into natural compounds.
Right. Now we shift from atmospheric and oceanic chemistry to the solid evidence, which you could, theoretically hold in your hand. The artificial rocks and the toxins.
Let's start with the classic industrial toxins like heavy metals, lead, mercury, cadmium.
The things we've been using in mining, smelting, and manufacturing for centuries.
And their big advantage in terms of detection is their permanence.
Their permanence is geological. Unlike organic pollutants, which, microbial action and natural chemical processes can break down over millennia, heavy metals are elements. They don't degrade. They can't.
They just change form.
They just change form. They get released during industrial activity, they're transported by wind and water, and they eventually settle, often concentrating in specific layers of sediment.
And these concentrations would stand out dramatically against the background noise of natural elemental concentrations.
Oh, absolutely. I mean, yes, there are natural deposits of lead or mercury, but industrial processing creates these massive anomalies, highly concentrated layers of these metals that are dispersed globally through aerosols and runoff.
And they can get trapped.
They become chemically trapped or chelated within specific mineral matrices in places like river deltas or deep sea clays. And a layer of high cadmium or high industrial lead, if it's preserved in an oxygen-poor environment, becomes a permanent detectable signature of large-scale metallurgy.
Okay, now we get to the really modern stuff. The truly modern and maybe the most challenging markers. The synthetics. The durable pollutants that just did not exist on Earth until we invented high-level chemistry.
This is where the Anthropocene really provides the sharpest possible contrast to deep time. We're talking about synthetic organic compounds that are incredibly robust.
Like plastics.
Most famously, microplastics. And also persistent fluorinated chemicals, PFCs, which are often called forever chemicals.
Microplastics are everywhere now. We find them from the top of Everest to the bottom of the Mariana Trench. But the worry is, as they degrade into these nanoscale fragments, won't they eventually just become, geochemically indistinguishable from the surrounding organic gunk? What's the source contention on their long-term persistence?
That's a really critical point, and it's something the sources address directly. While the largest pieces of plastic will likely be broken down or compressed into something unrecognizable, the sheer volume and the chemical complexity of the resulting plastic polymer fragments will persist.
So even at the nanoscale?
Even at the nanoscale, these fragments made of compounds like polyethylene or PVC, they retain their chemical heterogeneity.
Yeah.
Their structure is unnatural. They represent a layer of synthetic organic matter that is compositionally distinct from any natural biological detritus.
So they get bound up in the rock matrix.
And act as a time capsule of highly complex artificial chemical synthesis. They become a synthetic geological layer, proving advanced chemical engineering existed.
It's a layer of pure artifice.
Exactly. And the same goes for PFCs. They are built with these incredibly strong carbon-fluorine bonds that resist almost all natural breakdown processes. Heat, microbes, you name it. A layer enriched in those compounds just screams artifice in a way that almost nothing else does.
And we cannot overlook the most dramatic signal possible, the manipulation of the atom itself, radioactive signatures.
Right. Nuclear activity, whether it's civilian power generation or military tests, it leaves behind unique radioactive isotopes that are totally distinct from natural background radiation.
So it's not just a general increase in radiation, it's a specific fingerprint.
A very specific fingerprint. While short-lived isotopes decay pretty quickly, materials used in nuclear processing, particularly heavy synthetic elements like plutonium-239, they have half-lives long enough, we're talking tens of thousands of years, to be found preserved in the geological strata.
So finding those specific isotopes.
The detection of fission products or specific transuranic elements in sediments would be an unambiguous sign. It would signify a species capable of manipulating high-energy physics. It is perhaps the most definitive sign of advanced technology we could possibly imagine finding.
And finally, let's talk about the structures they built, the physical remnants of their world, which our sources cleverly term technofossils.
Technofossils,
Yeah.
the artificial rocks. These are complex manufactured materials like concrete, glass, and specialized metal alloys that are just not formed naturally in the Earth's crust. And crucially, they get permanently embedded in the geological strata.
Concrete is the ultimate example. I mean, it's the most widely used man-made substance on Earth. But how does something like a sidewalk persist geologically?
Well, first, concrete is an energy signature in itself. Its production, especially cement, involves heating limestone, which inherently releases a ton of carbon dioxide. But structurally, once it's formed, it becomes this durable, energy-intensive synthetic rock.
It resists natural processes.
It resists the typical diagenesis, the low-temperature processes that alter natural sediments in predictable ways. And even when concrete eventually breaks down, its distinct mineralogical signature, particularly the calcium silicate hydrate phases, remains utterly foreign to any natural sediment deposition.
So a future geologist coring into the Anthropocene layer would find this layer defined by a massive high-energy, chemically stable synthetic substance that just doesn't belong in the natural cycle.
And that layer would also contain vast quantities of alloy scrap, fractured glass, ceramics, materials that require tremendous heat and processing that simply does not occur in natural sedimentary environments.
So the geological record of a Silurian civilization would include a layer of rubble.
A layer of rubble and synthetic minerals that would defy any known natural geological explanation. It represents a massive planetary-scale investment of chemistry and energy to create complex, durable materials.
Okay, let's take a breath here. We've established this formidable list of evidence. We have specific isotope anomalies, heavy metal persistence, and the geological permanence of synthetic rocks.
It's a long list.
It is. Yet if all this stuff is so persistent, why haven't we found anything from a prior age, even one that existed, say, only 60 million years ago?
And here's where we introduce the concept of deep time as the great relentless eraser.
This is the central hurdle, isn't it?
This is what elevates the Silurian hypothesis from just a fun thought experiment into a really serious challenge for planetary science. We are searching for an incredibly thin, transient signal within a system, the Earth, that is a planetary scale recycler. It actively destroys its own archives.
Detail that geological recycling process for us. What specifically erases the evidence?
Well, the Earth is just. It's relentless. We are talking about massive geological mechanisms. Tectonic activity means that continents are constantly changing shape. Mountain ranges rise up,
Only to be immediately ground down.
immediately subjected to weathering and erosion, grinding their rocks into fine dust that gets washed away into the sea. Sediments get compressed, heated, and eventually they either get subducted, pushed down beneath another plate, or they get melted back into the magma.
So the evidence isn't just buried and forgotten. It is physically destroyed. It's unmade. It's integrated back into the mantle.
And the time scale for this destruction is just brutal, especially in the oceans. Our sources critically highlight this. The Earth recycles its entire oceanic crust about every 100 million years.
Every 100 million years, the whole ocean floor is new.
The whole floor. New crust is constantly forming at mid-ocean ridges, but the old crust is constantly being consumed with subduction zones.
Wow. So 100 million years. That means any deep sea archive, which is usually the most pristine, continuous record of climate history from, say, 150 million years ago, it's just gone.
It's gone, melted down. doesn't exist anymore.
So if a Silurian civilization existed far in the past, long before that 100 million year cutoff, the best, most globally distributed archive of its climate impact is completely unavailable to us.
Completely. We're restricted to looking for traces that just happen to be preserved in these extremely rare, stable continental cratons, the ancient hard shield areas of continents.
Which is not where you'd expect to find the best records.
Not at all. It's not where industrial civilizations tend to leave global continuous records.
And we also have to consider the relative fragility of civilizations themselves when you compare them to deep time.
Yeah.
Our current industrial civilization is what, maybe 300 years old? 500 if you really stretch it back to early metallurgy.
A technological society that lasts for even 100,000 years, which would be an incredibly impressive run, is still just a microscopic slash on a 500 million year geological canvas.
And if that civilization's main industrial period only lasts for a few thousand years,
then the resulting chemical signal is confined to an incredibly thin layer of sedimentation. A layer maybe only centimeters thick.
And what happens to a thin layer over 60 million years?
It gets blurred, it gets smudged. Post-depositional processes like, biological mixing, water infiltration, chemical reactions, they can diffuse that thin layer of evidence almost entirely into the natural background cycles.
So what survives is just fragments.
Truly fragmentary. It would require incredible luck, hyper-specific drilling locations, and detection technology with unbelievable specificity to confirm its artificial origin.
This immense difficulty, it leads us to the core scientific challenge, the confounding analog. Because Earth, all on its own, has natural ways of looking very much like an industrial planet.
Yes. How do we distinguish the industrial from the natural?
How do we tell them apart?
The sources focus specifically on one of the most compelling examples of natural planetary upheaval we know of, the Paleocene-Eocene thermal maximum, the PTM.
The PTM. Okay, tell us what that was and why it poses such a massive headache for the whole search for the Silurians.
The PTM happened approximately 56 million years ago, and it was a period of extremely rapid, geologically speaking, and intense global warming.
And
Crucially, the records show dramatic, fast isotope shifts, both the delta C13 and the delta O18 anomalies we were just talking about. And they are remarkably similar in their structure to what our current human industry is causing today.
So you're saying that 56 million years ago, the planet experienced a massive carbon release that chemically looks eerily like an industrial event.
Eerily like one, yes. Scientists largely agree the PTM was caused by a massive sudden release of carbon from natural reserves.
Like what?
Like vast quantities of methane clathrates, frozen ethane hydrate from the deep ocean floor, maybe triggered by volcanic activity or changing ocean currents. But estimates suggest thousands of gigatons of carbon were released.
Thousands of gigatons. That's massive in magnitude.
It is. It's huge. However, and this is the key insight that addresses the critique, while the magnitude of the PTM carbon release was perhaps 10 times greater than the total amount humanity has released so far,
the rate was different.
the rate of the PTM release was much, much slower. The PTM played out over several thousands of years.
And how does that compare to the Anthropocene?
Well, the Anthropocene is defined by a release of several hundred gigatons of carbon, but that release happened over just the last 200 years or so. This means the rate of carbon injection during our time is at least 10 to 100 times faster than the natural rate during the PTM.
And that super rapid, unnatural acceleration, that is the industrial fingerprint.
That's the tell. That distinction rate versus magnitude is the critical difference between a naturally high-impact event and an industrial-driven one. A Silurian society must have also triggered carbon release at an unnatural rate for us to be able to confirm it.
So if you find a massive carbon spike in ancient sediments, that's not enough.
Not even close. You first have to find those other non-natural markers, the plastics, the heavy metals, the concrete, the specific radioactive signatures, to confirm an industrial cause. If the evidence only shows the carbon and oxygen shifts, and the rate of change looks anything like the PTM,
It gets filed under natural climate event.
it gets filed under natural climate event regardless of its size.
That makes the geologist's job incredibly nuanced. The sources suggest that if a potential Silurian civilization lasted only briefly and didn't leave persistent plastics, but it did burn fossil fuels really fast, its signature might be perpetually obscure, just hidden within the natural range of the PTM analog.
It raises a really big sort of existential question. What is the minimum threshold of impact a civilization must leave to be geologically identifiable millions of years later.
Right.
Distinguishing a natural high-impact event from an industrial one is perhaps the single most important scientific challenge the Silurian hypothesis forces us to confront.
So if the evidence is so fragile and the Earth is actively destroying the majority of it through erosion and subduction, where do scientists even start looking? Where do you focus your efforts to find those continuous, undisturbed records? We need to talk about the deep archives of the Earth.
Yes, and the methodologies they employ. The hunt is necessarily focused on geological media that are characterized by long-term chronological fidelity and minimal post-depositional disturbance.
We have to find the Earth's quiet places.
That's it, exactly. We have to focus on the quiet places.
So let's start with what seems like the most critical archive for chemical history: deep ocean cores.
Deep ocean cores are absolutely vital. They're vital because they provide these long, relatively continuous records of climate history and chemical composition. They're taken using specialized techniques like piston coring.
Piston core.
Yeah, it's a device that drives a long barrel deep into the seafloor, and it retrieves this continuous column of sediment that can be hundreds of meters long.
And why are these sediments so much more useful than, say, sediments on land?
Well, on the deep abyssal plain, far from the continents, sediments accumulate very slowly and very steadily, layer by layer, year after year, completely undisturbed by the massive erosional chaos that's happening on land.
And these cores lock everything in.
Everything. Atmospheric composition, ocean chemistry, magnetic pole shifts for dating, and crucially, the shells of those deep-sea foraminifera, the very biomarkers that record those carbon and oxygen isotope ratios.
So if a civilization left a global trace of heavy metals or unusual isotopes that spread across the planet, those deep ocean cores are the most likely place to find that single, uninterrupted sedimentary layer, perfectly stacked in chronological order.
They are the global standardized thermometer and chemistry set for planetary history.
Yeah.
Provided, of course, that the sample is less than 100 million years old and hasn't yet been subducted.
Okay, that's a big caveat.
A huge one.
Next, we have the polar ice cores. They offer a different but an equally valuable snapshot of atmospheric history.
Ice cores are amazing. They're retrieved from places like Antarctica and Greenland, and they are, quite literally, atmospheric archives. As the snow falls and compacts into ice, it traps these tiny bubbles of ancient air,
Along with anything else in the air.
along with atmospheric particulates, aerosols, dust, pollen. This creates an unparalleled chronological record of what the atmosphere was actually made of.
How reliable is the dating for ice cores? I mean, can you get that same kind of resolution?
For the recent past, it's even better. Ice cores are often dated using highly reliable annual layers, just like tree wings. So you get exceptional temporal resolution going back hundreds of thousands of years.
So if a Silurian civilization polluted the air with massive amounts of sulfur dioxide or soot or specific gases, those particulates would be chemically trapped in the ice.
And we could pinpoint the exact year of the industrial spike.
So the ice cores tell us about atmospheric pollution and greenhouse gas spikes, while the ocean cores tell us about ocean chemistry and temperature shifts. What about the land masses themselves? You said they're chaotic, but we have to look there, right?
We do. We have to look at river deltas and wetlands.
Why there specifically?
Because these continental areas, they act as enormous geological sinks or traps. River systems are constantly washing down heavy metals, organic residues, and sediments from the continental land masses. When this material reaches a delta or a wetland, it often settles in environments that are anoxic.
Oxygen starved.
Right. And why is an anoxic environment so critical for preservation?
The lack of oxygen prevents things from breaking down. It stops the microbial action and oxidation.
Exactly. So the synthetic organic chemicals, the heavy metals, the technofossils that get swept down from industrial centers can be preserved in these dense, low-oxygen sediments far, far better than they would be in dry, aerated soil, which is so prone to erosion and chemical alteration.
Meaning, if a heavy industrial zone was located in a massive river valley, its concentrated heavy metal runoff and its synthetic wastes could be trapped and preserved in that delta layer. It would provide a strong, localized signature even after the original city is long, long gone.
They are the geological equivalent of a sealed vault for pollutants. They offer a concentrated regional signal that can often resist the later blurring that affects the thinner global signals.
And finally, to connect all these disparate archives, the ice, the ocean, the delta, you can't just look at one. Scientists require what? Global geochemical surveys.
This is the methodology for synthesis. You're not just looking for one weird layer in one place. You have to be engaged in a broad, comprehensive search that is focused specifically on finding unusual, widespread, isotopic patterns that defy any known natural explanations.
So the confirmation of a Silurian event wouldn't be one scientist finding one plastic bag in one core somewhere.
Absolutely not. It would be a career ender to claim that. It requires finding that telltale combination.
The whole fingerprint.
The whole fingerprint. A rapid, synchronous negative delta C13 spike combined with a delta O18 warming signal correlated with anomalous layers of heavy metals and, crucially, synthetic technofossils. And all of it appearing simultaneously across multiple geographically separated archives.
That synchronized global signal is the only way.
It is the only way to confirm planetary-scale artificial industrial activity. Anything less is just an interesting anomaly.
Okay, we've thoroughly covered the what to look for, the where to look, and the brutal mechanisms of geological erasure. But let's shift gears a little. The researchers who proposed this hypothesis, they weren't necessarily expecting to find ancient reptilian artifacts.
Not at all.
So if we connect this to the bigger picture, what is the profound current value of the Silurian hypothesis? What's the so what of this entire thought experiment?
The primary value of the Silurian hypothesis is, maybe surprisingly, not about proving ancient civilizations existed. It's about using the distant past as a mirror to understand our present.
Right.
It's a scientific exercise that profoundly impacts how we define, measure, and predict the legacy of the Anthropocene, our current age.
So it's fundamentally about sharpening the tools we use to understand our own irreversible impact on the planet right now.
Precisely. By forcing scientists to define the precise minimum criteria needed to detect an industrial civilization millions of years after it vanished, they have to rigorously refine their methods for recognizing the permanent impact of our own civilization.
We're stress testing the geological template for industrial activity against the harshest standards imaginable. Deep time.
That's a powerful way to put it. It forces us to define what makes the human age geologically unique. We have to go beyond just general warming to these very specific chemical proxies. We have to identify the specific materials, the isotopes, the plastics, the concrete, that are robust enough to last 60 million years.
And in doing so, that helps us understand the true scale and the permanence of what we are doing today.
We are, in essence, defining the golden spike of the Anthropocene. We are providing future geologists, those who might exist millions of years from now, regardless of their species, with the ultimate roadmap for how to identify our activity.
We're writing the instruction manual for the people who will dig us up.
We're defining the signature they will seek out and the exact chemical parameters of that search.
So if we fast forward 60 million years, what does that roadmap tell us about our future legacy? What will future geologists definitively find when they core into the layer of rock that represents our time?
Well, they will find specific, unmistakable signs that our sources delineate with really scientific certainty. First, the widespread global distribution of plastics and PFCs integrated into the sediment layers as a form of synthetic organic matter.
Right, the forever chemicals and the plastic fragments.
Second, the unique isotope shifts in carbon and nitrogen that mark our burning of fossil fuels and our reliance on synthetic farming. The telltale signs of rapid, unnaturally accelerated biogeochemical cycles.
And perhaps most visibly, the sheer abundance of technofossils.
Oh, that later will be defined by concrete, glass, steel alloys, and fly ash, the high-energy byproducts of massive global manufacturing. These materials exist in such vast quantities, and they possess such chemical and structural heterogeneity that they instantly defy any natural geological explanation.
That layer of rubble and synthetic material, it will be global, not regional.
And that signifies a planetary-scale industrial society.
This research, it forces us to confront the lasting permanence of our current actions, even when you compare it against deep time. We understand now that we are not simply building things that last 1,000 years. We are creating chemical and geological markers that will endure for millions of years.
Long after our species is gone or dramatically changed,
Yeah.
just consider the massive material flows. The amount of concrete we produce annually now surpasses the total amount of biomass the entire world produces.
That's an incredible statistic.
It is. We are shifting from a geological age that's defined by biology and climate to one defined by complex, synthetic, technologically mediated materials.
The philosophical lesson here is one of proportion and humility, isn't it? The sheer knowledge that the byproducts of our everyday convenience, our plastic water bottle caps, the slag from our steel production, the chemical residue from our fertilizers, that all of that could theoretically be compressed and preserved into a telltale layer of sediment, marking the 21st century for a civilization 60 million years from now.
Huh.
that profoundly shifts our perspective on what a legacy really means.
It absolutely does. The hypothesis reminds us that civilizations are fragile, that technological time is vanishingly brief, and that the vast mechanisms of the earth erosion, subduction, recycling are the ultimate forces of erasure.
What survives of us won't be our names.
It won't be our names or our stories. It will be the sheer, inert, chemically unique material we left behind. We are carving our mark, yes, but we are doing it on a canvas that is constantly being consumed and overwritten.
This has been an incredible deep dive, moving from fictional inspiration all the way to rigorous scientific methodology. We've examined what it takes for a civilization's echo to survive deep time.
Yeah.
We've discussed the specific industrial signatures, the light carbon isotope anomaly, the delta C13, the rapid temperature spikes seen through oxygen isotopes, delta O18, and the nitrogen cycle disruption from synthetic fertilizers.
And we thoroughly covered the geological permanence of those technofossils, the concrete, the glass, the alloys, and pollutants like heavy metals and robust microplastics.
And crucially, we analyzed why finding anything is so incredibly difficult. We cited the 100 million year oceanic recycling cycle and the confounding nature of powerful natural events like the PTM.
Emphasizing that the rate of change, not just the magnitude, is the true industrial fingerprint.
And ultimately, the real value of it all, using the Silurian hypothesis not to find ancient secrets, but to sharpen our understanding of the Anthropocene and acknowledge the indelible, permanent legacy we are etching into the rock record right now.
Perhaps no civilization came before us. Perhaps we really are the first to carve our mark so deeply into the geological record, altering the planet's chemistry faster than any known natural event. But the hypothesis leaves us with this final provocative thought to consider. If a civilization lasts for only 10,000 years and then vanishes, and its geological layer is subjected to millions of years of erosion and tectonic erasure, what fundamentally is the difference between that ancient, vanished industry and a powerful, short-lived natural carbon event? The enduring question is not whether the Silurians existed, but what voice our own layer of plastics, concrete, and isotopes will speak for us in the deep future once we are silent. Civilization. We tend to define ourselves by it, don't we? You know, the cities we build, the languages we speak, this profound machine-driven age we find ourselves in. We call it the Anthropocene, the age of humans. But just pause for a second and think about the idea at the heart of our deep dive today. What if this industrial age, this thing that feels so codal, so singular, isn't the first?
That is the entire question, isn't it? We're asking you to try and step outside of human history for a moment and look at geological time.
It's a huge shift in perspective.
It really is. I mean, consider the possibility that deep beneath our feet, maybe 50 million years ago or even 300 million years ago, there's a faint echo, an almost completely erased trace of another industrial age.
Another civilization.
Maybe. A civilization, maybe not like us at all, that harnessed energy, that built things, and then it vanished.
It sounds like pure science fiction. I mean, it's a phenomenal premise, but the thing that makes it so compelling, and what we're going to dig into, is how grounded it is in actual physics and geology.
Exactly.
Our mission today is to really analyze the source material you've provided and get into this incredible geological detective story. It's called the Silurian hypothesis.
Right.
We're going to try and understand exactly how scientists would even begin to determine what traces physical, chemical, isopic, long-dead industrial civilization might have left behind. And maybe more importantly, why finding them is, well, it's an almost impossible task.
We're using the present to interrogate the past. That's the key. And, this isn't some search for Atlantis or ancient myths.
No.
This is a systematic study of persistence. We are analyzing what signatures are durable enough, robust enough to survive tens of millions of years of the Earth's relentless recycling processes.
And to be clear on where this came from, this isn't from some ancient text. The hypothesis was formally proposed very recently in 2018.
That's right, by astrophysicist Adam Frank and the very well-respected climate scientist Gavin Schmidt. It's pure modern scientific inquiry.
But the name doesn't sound very scientific.
No, and that's the fun part. While the intellectual rigor is incredibly high, the name has a delightful pop culture origin. The sources mention it was inspired by a fictional race from the classic Doctor Who series.
The Silurians.
The Silurians, exactly. A race of intelligent reptilians that were imagined to have built this complex society long, long before humans ever evolved.
I love that. I love that blend of, high concept science and a fun, accessible hook. But as you said, and this is crucial, we have to immediately separate the scientific thought experiment from the fiction. The sources are absolutely crystal clear on this point.
They are.
This is purely about detectability. That's the word. If a civilization existed, if it used vast amounts of energy, what would its geological scar even look like?
And that forces us to use the Anthropocene, our current age of, profound human impact, as a kind of measuring stick. It sharpens our own definition of what the geological signature of rapid, global, energy-intensive activity actually is.
So we turn the lens back on ourselves.
We have to. If we disappeared tomorrow, what would be left of us in, say, 60 million years? And if we can define that signature clearly, well, then could we be misinterpreting a similar natural-looking shift from 50 million years ago?
That reframes the entire mission then. It's not about finding lizard people under the Earth's crust.
No, not at all.
It's about testing the absolute limits of the geological record itself.
Exactly. We're trying to understand the signal-to-noise ratio in deep, deep time.
Okay, so let's really unpack this. If we assume, just for the sake of the thought experiment, that some advanced industrial civilization was around for, let's say, 50,000 years.
A decent stretch of time.
Right. They had machines, vast energy needs, maybe global cities, and then they vanished completely. What are the specific, measurable, persistent signs that geologists today would actually be looking for? We need to get into the scientific nuts and bolts of what truly lasts in the rock record.
This is really the core synthesis of the sources. The idea is that industrial activity leaves a whole suite of signatures that are so distinct they are highly unlikely to be produced by purely natural processes.
Or at least not all at once.
Not in combination, exactly. We can break these persistent signs down into 7 key categories that would endure in the rock layers. Think of it as a checklist for a geological crime scene.
A crime scene checklist. I like that.
Yeah.
So where do we start with the big stuff? The ruins of cities?
Actually, no. We start with the most subtle, but maybe the most globally distributed markers, the isotopic anomalies. These are chemical clues that you'd need a lab for, not a big archaeological dig.
Okay. Isotopic anomalies, chemical markers. Lay it out for us.
The first and probably the biggest signature is the carbon isotope signature, specifically something called the 13C anomaly.
Delta 13C.
Right, and this is absolutely critical because carbon is, it's the currency of an industrial society. It's the backbone of our energy, our materials, our life.
And the sources detail that this is the distinct fingerprint left behind when you burn massive amounts of fossil fuels. But for everyone listening, we should clarify the mechanics here. What's the fundamental difference between the carbon that's locked up in ancient oil and coal and the carbon that's just, cycling in the atmosphere today?
Great question.
Why does burning that ancient stuff specifically change this isotopic ratio?
Okay, so it all hinges on the difference between the two main stable isotopes of carbon, carbon-12 and carbon-13.
Okay.
Carbon-12 is the lighter one, and it's far, far more common. Carbon-13 is a little bit heavier. Now, when plants perform photosynthesis, their metabolic machinery, it's surprisingly efficient, and it shows a slight preference for the lighter carbon-12 atom.
It's just easier for them to burn.
It's faster for them to grab and use C12. So over a plant's lifetime, it builds its tissues, its leaves, its stems with a slightly higher ratio of C12 to C13 than is found in the atmosphere.
Okay, so plants are basically picky eaters for carbon. They prefer the light stuff.
That's a great way to put it. So when that plant dies and then gets buried and over millions of years becomes part of coal or oil or natural gas, that entire reservoir of stored carbon is naturally enriched in the lighter carbon-12.
Right, so all our fossil fuels are basically concentrated ancient sunlight stored in this isotopically light carbon.
Precisely. This carbon is geologically sequestered. It's locked away underground, taken out of the active cycle for millions upon millions of years. When a civilization ours, or a hypothetical Silurian one, comes along and extracts and burns massive amounts of these fossil fuels,
we're rapidly re-injecting all of this ancient light C12 back into the atmosphere and the oceans.
And the key words there are rapidly and massive. The speed and the sheer volume of this injection is so fast that it completely overwhelms the system's ability to rebalance itself naturally.
It's like pouring a whole bottle of black ink into a small glass of water.
Right.
It just changes the color instantly.
Exactly. This rapid introduction of light carbon shifts the global ratio. The atmosphere and then the subsequent layers of sediment that form in the oceans and lakes become isotopically lighter.
And that's what's measured as a negative 13C anomaly.
That's it. You'd see a sudden, really pronounced drop in the ratio of carbon-13 to carbon-12 in the sediment layer that corresponds to that industrial era. That is a geological marker that just screams rapid, high-energy input. It doesn't look like slow, background biological activity.
But hang on, let's push back on that a bit. You said the speed is crucial, but what is a huge natural volcanic event like the Siberian traps or something spread out over 1,000 years also caused a big, rapid carbon release? How do we distinguish the industrial fingerprint from a natural one just based on that carbon spike?
That is the core challenge, and it's something we're definitely going to tackle head-on later when we talk about the PTM. But for now, the immediate difference is likely the scale and the synchronicity with other markers. While massive volcanism does release carbon, it often comes with other very specific geological signatures, thick layers of ash, specific sulfur deposits, and it generally lacks that clean, powerful C12 bias you get from burning ancient organic matter.
So the flavor of the carbon is different.
The flavor of the carbon is different. An industrial age fueled primarily by extracted organic carbon has a very distinct, consistent global signature. And the suddenness, a shift happening over decades or millennia rather than hundreds of thousands of years, is highly suggestive of an external driver, whether it's a methane clathrate event or a civilization.
Understood. So the speed and the specific isotopic flavor are the first big clues. Moving beyond the carbon then, the sources also point to temperature shifts, which we can track using the 18O record.
Yes, the temperature spikes. These are reflected in the oxygen isotope records, or 18O, and they're the next piece of the puzzle. Industrial activity, especially if it's based on burning massive amounts of carbon, will inevitably trigger rapid global climate warming. We're, of course, seeing this play out right now.
So in the geological record, we aren't just looking for warmth. We're looking for a sharp global spike that completely breaks the slow-moving natural climate trend.
Correct. The ATDO value that we measure in things like marine carbonates, the shells of tiny sea creatures, reflects two main things. The total amount of ice volume on Earth.
Right, because lighter oxygen gets locked up in ice sheets.
Exactly. And it also reflects the temperature of the ocean water itself. So when the Earth rapidly warms, continental ice sheets melt, releasing that light oxygen back into the oceans, and the ocean temperature itself increases. Both of these factors shift the ATDO value dramatically.
So if a hypothetical civilization was around for, say, 50,000 years, used massive amounts of energy and then collapsed, either because of or after a climate crisis, that entire warming period would be etched into the strata as a distinct rapid thermal maximum.
Yes. A rapid spike of maybe 5 to 10 degrees Celsius over just 2,000 or 3,000 years would be highly visible, and it would be a global signal.
It would be a huge, unmistakable environmental shock recorded in the very chemistry of the water, which is then preserved in these ocean sediment cores.
And if you can combine that thermal spike with the negative carbon isotope shift happening at the exact same time in the same layer of rock, the correlation becomes incredibly powerful.
Okay, that makes sense. And the third major chemical signature the sources mentioned relates to disrupting the nitrogen cycle, which is measured through 15N. When I hear industrial nitrogen, my mind immediately goes to agriculture, to feeding billions of people.
And that's exactly the link. We're talking about the industrial fixation of atmospheric nitrogen. It's the chemical process used to create synthetic fertilizers.
The Haber-Bosch process.
Haber-Bosch process. Today, this process takes inert nitrogen gas from the air, which is about 78% of our atmosphere, but mostly unusable by plants, and converts it into ammonia, which is essential for modern agriculture.
And it's incredibly energy intensive. It's a perfect signature of an industrial process.
It is. And crucially, it fundamentally alters the natural nitrogen cycle. Naturally, nitrogen fixation happens mostly through bacteria in the soil or through lightning strikes. And these processes have a certain stable isotopic signature for nitrogen, the 15N value.
But the industrial process is different.
Radically different. It introduces massive, and I mean massive, volumes of bioavailable nitrogen into the environment with a profoundly different 15N signature.
So we're basically force-feeding the entire global soil and water system with billions of tons of nitrogen that has an unnatural isotopic composition.
Exactly. This activity alters the I-15N ratio in soils and river sediments, even in ice cores. It leaves a unique industrial scar far beyond what natural cycles usually achieve. So if a past civilization had highly productive, intensive agriculture based on synthetics.
The change in 15N would serve as a crucial third piece of interlocking evidence.
Right. It demonstrates not just energy use from the carbon or climate change from the oxygen, but technological manipulation of the planet's fundamental biogeochemical cycles.
So we have this chemical trinity: carbon, temperature, and nitrogen. But industry also means waste, often in the form of incredibly persistent and often toxic substances.
And what's really fascinating about the persistence of some of these materials is that in many cases, they were designed to last. From a geological perspective, some of the things we throw away are actually tougher than the environment itself.
Okay, so let's start with the classic pollutants, heavy metals. We're talking about elements that exist naturally, but only industry really concentrates them to these unnaturally high levels.
That's the key. We're looking for industrial toxins that persist and are measurable in rock layers, things like lead, Pb, mercury, Hg, and cadmium, Cd.
Right.
While these elements are, naturally occurring in the Earth's crust, processes like mining, smelting, and manufacturing concentrate them and then distribute them globally in layers far, far exceeding natural background levels.
And the distribution is the giveaway, isn't it? We're not looking for a localized ore deposit. We're looking for a thin, global layer of elevated contamination showing up at the same time in sediments in the Arctic and in the deep Pacific.
Precisely that. If you look at our own history, even the small-scale lead smelting done by the Roman and Chinese empires left measurable, albeit very subtle, lead traces in Greenland ice cores.
Wow.
So a truly global industrial civilization would leave a dramatic spike in these heavy metals, an unnatural spike in concentration, maybe 100 or even 1,000 times higher than the surrounding layers. And these contaminants, they don't really decay, they just redistribute and persist, often locked into clays and sediments, providing an incredibly resilient geological marker.
That brings us to the materials that really define our current age: plastics and other synthetic compounds. The sources note that things like microplastics and fluorinated chemicals are embedding themselves into our current strata right now as we speak.
This is perhaps the most unmistakable non-biological signature of the Anthropocene. Plastics are artificial polymers. They are characterized by chemical structures that are highly, highly resistant to natural biological and chemical decay.
And we know microplastics are now everywhere.
They're globally distributed, they're sinking into the deepest ocean sediments, they're mixing with terrestrial soil, all at staggering volumes.
And the sources really emphasize that from a future geologist's viewpoint, the chemical structure itself is a dead giveaway. Nature just doesn't produce polyethylene or nylon.
Absolutely. The same goes for the highly persistent fluorinated chemicals, PFAS, what people call forever chemicals.
Right.
These compounds contain carbon-fluorine bonds, which are among the strongest chemical bonds in all of organic chemistry. They are manufactured chemicals with structures that simply did not exist naturally on Earth until the 20th century.
So if a past civilization had a similar kind of chemical industry, finding a layer that contains those complex synthetic polymer or fluorinated chemical residues molecules robust enough to survive millions of years, that would be an unambiguous sign of technology.
It would have to be. It would require sophisticated chemical synthesis, high energy input, and a global distribution network. It's arguably the most specific, non-natural signature we could possibly leave behind.
And then we move to, well, to the most dramatic and in some ways the most chilling signature of all: radioactive isotopes.
Right. This refers to the evidence of potential nuclear activity. Whether a civilization harnessed nuclear power for energy generation or, heaven forbid, developed nuclear weapons, these processes create unique isotopic signatures that are fundamentally distinct from natural decay chains.
Let's just clarify the difference for a second. Natural radioactivity comes from elements that have been here since the Earth formed, like uranium-238 and thorium-232. They have half-lives in the billions of years.
Exactly. They're part of the Earth's primordial heat source. But nuclear reactors and weapons, they create a whole different zoo of short-lived isotopes through processes like fission and neutron capture.
So the presence of specific man-made elements, like, say, plutonium-239 or cesium-137, or certain ratios of iodine and americium, finding those in a sediment layer is a complete giveaway.
It's a complete giveaway. These isotopes simply do not occur naturally in these quantities or these specific ratios.
It really is the ultimate smoking gun, isn't it?
It is. If a previous civilization utilized nuclear technology, even for a brief period, the distinctive decay products would be preserved in the geological record. It would be a completely non-natural isotopic pattern, impossible to explain through standard geology or background cosmic radiation. It provides the highest level of certainty regarding intelligence and technology.
Okay, so we've covered the subtle chemistry, the invisible pollution, the radioactive fallout. Now let's talk about the physical stuff. The buildings, the machines, the actual debris that gets mixed into the rock layer. The sources use this excellent term, technofossils.
Yes, technofossils. They're defined as synthetic, artificial rocks embedded in the strata. So now we're moving from microscopic chemical traces to macroscopic physical evidence of engineered materials that defy natural geological formation.
And the key here has to be durability and synthetic composition, right?
Okay.
So give us some of the specific, robust examples that the sources highlight.
The primary candidates are materials like concrete, glass, and various alloys. Let's start with concrete.
Yep.
It is, for all intents and purposes, an artificial rock. We make it by combining aggregates like sand and gravel with cement, which itself requires a massive high-temperature industrial process, the calcination of limestone.
So it's fundamentally non-natural chemistry.
It is, and it's designed specifically for durability. A future geologist could look at a fragment of concrete, analyze its chemical makeup, and know immediately that it didn't form through volcanic activity or normal sedimentation.
They could see the recipe.
They could see the recipe, they could analyze its chemical composition, the specific ratio of calcium, silicon, and aluminum oxides, and recognize it as a material produced in an energy-intensive industrial furnace.
And what about glass?
Similarly, industrial glass, which is incredibly pure silica, is very resilient to chemical weathering. Now, nature does create glass. Volcanic obsidian is one example.
Right.
But industrial glass has a uniform, high-purity composition that reflects complex manufacturing control. It's too clean, too perfect to be natural.
And then the metallic remnants,
Yep.
alloys.
Yes. Alloys are complex mixtures of metals that just don't occur naturally in that mixed state. If a geologist found a seam containing fragments of, say, aluminum metal or stainless steel or specific bronze alloys in a 50-million-year-old layer, that material simply could not have formed there naturally.
That distinction is so important. Finding a chunk of iron ore is natural. Finding a fragment of steel alloy, which is iron mixed with specific amounts of carbon and maybe chromium, all cooked under intense heat. That's a sign of intelligence in industry.
They are durable, synthetic, and they would be unmistakable signs of intelligence even if they were heavily fragmented or corroded or chemically altered over eons. The fact that the materials are engineered through complex, non-biological chemical synthesis is what elevates them to the status of a technofossil.
So if we just recap, we have 7 clear, persistent fingerprints. These isotopic shifts in carbon, oxygen, and nitrogen. Heavy metal spikes, persistent synthetics like plastics and forever chemicals, radioactive markers, and these durable technofossils. That is a massive, multifaceted amount of potential evidence.
It is a phenomenal checklist. It really is. But, and this is a huge but, here's where it gets really interesting. This is where we move from the detective's toolkit to the challenges of the crime scene itself.
Right.
Despite these 7 specific, powerful fingerprints, the source materials are very clear that finding them is nearly impossible. We have to grapple with the geological reality of time and a very, very active planet.
So the list of evidence is powerful, but it's all based on the premise that the Earth is some kind of stable archive, just neatly filing away layers of history.
Which it is not.
And the sources suggest it's the exact opposite. So let's pivot now to the immense challenges of geology itself. Why finding even 7 smoking guns is an almost impossible task.
We have to synthesize this concept of the restless Earth and the sheer, almost ungraspable vastness of time. I mean, if you try to visualize Earth's 4.5 billion year history as a single calendar year, our entire human industrial civilization is less than the last second of New Year's Eve. A civilization that lasted for even 100,000 years is a microscopic moment in that year.
So we're looking for an extremely thin, fragile layer of evidence that's been subjected to immense pressure, heat, compression, and movement for millions upon millions of years.
This is what the sources refer to as the global eraser mechanism. There are 2 major, relentless forces that are constantly destroying and resmelting the evidence.
The first one detailed in the source is this fundamental process of oceanic recycling.
Yes. The vast majority of our industrial waste, our sediments, all our evidence today ultimately settles onto the seafloor. That's its final resting place.
But it doesn't rest for long.
Not in geological terms. The Earth's lithospheric plates are constantly in motion. New seafloor is created at mid-ocean ridges, and old seafloor is destroyed at subduction zones. And the sources detail the specific rate. The oceans completely recycle their entire floor roughly every 100 million years.
So any evidence,
Yeah.
all the microplastics, the heavy metals, the sunken ships, the deep-sea communication cables, anything that settled onto the seafloor 110 million years ago is just gone.
It's gone, cooked and melted back into the Earth's mantle.
Wow.
I mean, think of the Pacific plate diving under the Japanese archipelago. That plate is carrying with it sediments, metals, and potentially every artifact that was dumped there for up to 100 million years. It's a vast, slow-moving conveyor belt carrying everything on a 100-mile journey down into the mantle, where the rock, the plastic, and all the chemical data are literally melted and reintegrated into the planet's structure.
It eliminates the most common resting place for global pollutants in deep time.
It does, and the second major force acting on the evidence is continental erosion.
So, on land.
On land, the process is different, but it's equally destructive. Mountains rise up because of tectonic collisions, but from the second they start rising, they are subject to relentless weathering rain, ice, wind, chemical erosion. Cities are pulverized, riverbeds shift over vast areas, and rock layers are exposed, eroded down to sand, and then reformed somewhere else, often completely unrecognizable.
So the evidence isn't melted, it's pulverized and diluted. It's like a geological washing machine, constantly scrubbing the continents clean.
And what survives is therefore highly fragmentary and incomplete. We are not looking for a pristine layer. We are looking for tiny, isolated pieces of a story that was once globally distributed.
Which brings us back to the time factor. If a hypothetical civilization lasted for only, say, tens of thousands of years, that's a geologic blink of an eye.
It's almost instantaneous. The sources note that a civilization lasting that short a period could vanish almost entirely. And the evidence that does survive faces two huge issues. First, there's dilution.
Right.
The succeeding millions of years of natural sediment deposition will just overwhelm and dilute that thin industrial layer, making it harder and harder to spot.
And the second issue.
The second is that the traces become blurred into natural cycles. If an isotopic shift only lasted for 20,000 years, the subsequent 50 million years of natural carbon cycling will overwhelm that signal until it's nearly undetectable against the background noise.
So this is the critical juncture for our geological detective.
Yeah.
How do you distinguish a massive, fast, but short-lived industrial event from a massive, fast, but short-lived natural event?
And that leads us directly to the core analytical challenge of the whole hypothesis, the case study of natural lookalikes. The sources remind us that natural processes on Earth have created climate shifts that, on the surface, mimic what we are doing today.
And the classic example that's always cited in the research, the perfect foil to the Silurian hypothesis, is the Paleocene-Eocene thermal maximum, the PTM.
The PTM.
We need to locate this precisely in time.
It occurred approximately 56 million years ago, and it stands as one of the most rapid, profound, and extreme global warming events that we know of in the geological past. It is a perfect natural analog for the type of rapid change an industrial civilization might induce.
Let's really detail the similarities, because this is where the distinction gets so tough. Why does the PTM look so much like an ancient industrial society's footprint?
Well, it shows nearly all the core climate and carbon markers that we just discussed. Global temperatures soared by about 5 to 8 degrees Celsius in just a few thousand years.
That's incredibly fast.
A very rapid spike, just like our current warming trend. And most importantly, it caused a massive negative E13C excursion.
Wait a second, a negative E13C shift means the carbon cycle suddenly became enriched with light carbon-12. That is the exact fingerprint we said results from burning ancient fossil fuels.
It is the same carbon fingerprint. Geologists believe the PTM was likely triggered by the massive rapid release of carbon specifically from methane hydrates or clathrates that were stored in the deep ocean floors.
Frozen methane.
Frozen methane, yes. Initial warming probably destabilized these vast icy reservoirs, leading to a runaway release of methane, which is an incredibly powerful greenhouse gas, which then oxidized into carbon dioxide.
And the amount of carbon that was injected into the atmosphere was immense. It was comparable in speed and scale, if not the total volume, to what humanity is doing right now. And it resulted in ocean acidification, global warming, all etched into that rock layer 56 million years ago.
And so the challenge becomes crystal clear. If a future geologist saw the PTM layer, how could they definitively say this was a massive methane release and not this was the rapid collapse of a prior civilization? They both show the warming spike and the light carbon injection.
So distinguishing natural shifts, like the PTM, from truly industrial shifts is the central difficulty of the Silurian hypothesis.
It really is, and it comes down to needing those multiple interlocking markers. The PTM provides a clear climate shift and a carbon isotopic shift. But to prove a civilization, you have to find the non-natural signatures that defy a purely natural explanation.
The other 5 markers.
You need the carbon spike, plus the synthetic chemicals, plus the heavy metal layer, plus the radioactive materials, plus the technofossils, all coinciding in that same thin layer.
So the detective work relies not on finding one smoking gun, but on the coincidence of all 7 different types of persistent, non-biological evidence showing up simultaneously. It has to be a robust, multi-layered fingerprint.
Exactly. The Silurian hypothesis forces us to understand that the background hum of natural geological activity is itself enormous. We are looking for a very unique, synthesized melody in the middle of a global orchestra.
Okay, we've defined the magnitude of the challenge. The evidence is fragmentary, it's erased by the oceans, it's confused by natural events like the PTM. So if we were to launch a global research project to actually test this hypothesis, where on earth would we look for these hidden traces? And, what does this colossal thought experiment ultimately teach us about our own fleeting place in Earth's timeline?
Well, given the destructive power of all these geological forces, the search strategy has to be incredibly targeted. You can't just dig anywhere. We're looking for what you might call geological safe deposit boxes, places where long, continuous geological records have been miraculously preserved from erosion and subduction.
The sources outline a few key areas where we might find these records, protected from that global eraser. The first one mentioned, and it seems maybe the most valuable, are deep ocean cores.
Yes. Deep ocean cores offer the highest potential for continuous records of climate and chemistry. And that's primarily because they minimize the disruption from surface erosion, while, as we said, the vast majority of the seafloor gets subducted.
There are some spots that are stable.
There are some stable abyssal plains and continental rises where sediment deposition is slow, continuous, and has been relatively undisturbed for periods that can approach 150 million years.
And that stable, cold, dark environment is key. It must act as a great chemical preservative for things like heavy metals or microplastics, or even specific biological residues that settle out of a water column.
They are essentially uninterrupted archives of global atmospheric and oceanic conditions. So yes, we would be drilling these long cores and then analyzing them inch by inch, looking for those sharp synchronous changes in chemistry, the sudden spike in lead, or that negative carbon excursion.
Our second key area for finding preserved material is where the evidence might be physically trapped and frozen: polar ice cores.
Ice cores are incredibly valuable because they provide a direct, high-resolution chemical archive of the atmosphere itself. They're like atmospheric time capsules. As snow falls year after year, it traps tiny bubbles of air, dust, and aerosols from the atmosphere at the moment it fell.
This gives us a direct, highly resolved record of atmospheric composition. So if a prior civilization caused massive spikes in greenhouse gases or specific industrial aerosols like soot or sulfates from coal burning, those tiny bubbles of air trapped in the ice would preserve that signature directly.
Exactly. And furthermore, many persistent man-made chemical residues would also get trapped in the ice, preserved in a chemically inert frozen state for immense periods. Provided, of course, that the ice cap itself survives the intervening millions of years of climate change.
A big if.
A very big if. But it would allow for chemical dating with remarkable precision, assuming the core is continuous.
Okay, so moving away from the poles and the deep sea, the third location targets these large accumulation zones on the continental shelves, river deltas and wetlands.
These are geological sinks. They are low-energy environments where vast quantities of sediment are carried downriver and deposited rapidly, which buries material and can prevent oxidation and erosion.
You think of the massive Mississippi Delta or the ancient river deltas of Asia. They're just accumulating huge amounts of material every single year, layering it and preserving it.
They are excellent places to search for specific heavy residues, heavy metals, organic pollutants, and even fragmented technofossils that were washed down from continental landmasses. If a civilization was smelting metals on a large scale or using synthetic fertilizers near coastal regions, these rapidly accumulating sediments would preserve those chemical layers in a relatively thick, easy-to-read geological book.
So we target these specific archives: deep ocean for global chemistry, ice cores for atmospheric composition, and river deltas for terrestrial pollutant runoff. The last strategy mentioned is a bit broader: global geochemical surveys.
This is the systematic, big picture approach. It involves pooling data from all the existing geological databases worldwide and using computers to search for unusual isotopic patterns on a global scale. You wouldn't be looking for a single city or an artifact. You'd be looking for a sharp, synchronous, global change in signatures like 13C or A15N in multiple core samples taken across different continents and different environments.
It's the coincidence that matters again. The confirmation that a chemical anomaly wasn't local, like a single volcano, but a globally synchronized event. That points to a globally interconnected cause, whether it's natural, like the PTM, or industrial, like the Anthropocene.
And that brings us perfectly to the deeper implication of all this. The sources are very clear. The Silurian hypothesis isn't really about finding ancient history. It's a thought experiment that serves a profound and immediate purpose.
It's fundamentally about perspective. The core value lies in sharpening our tools for recognizing and defining our own impact, the Anthropocene, before it becomes unrecognizable geological noise.
We are using the past as a lens to understand the present. By asking, what trace would they have left if they're operating at our scale? We are forced to define exactly what we are doing now in rigorous geological terms.
We're connecting the two ends of the timeline. The sources emphasize that by detailing the necessary markers for a vanished industry, scientists gain an incredibly clear definition of what we're doing right now that is truly unique and persistent.
Let's take the PTM again. Nature can create the carbon isotope shift. It can create the warming. But nature does not create robust fluorine-bonded chemicals. Nature does not refine aluminum metal or create Portland cement. By defining the unique, non-biological suite of signatures that must persist, we gain a much clearer picture of the magnitude and the quality of human influence today.
We're essentially writing the textbook for future geologists to read, which leads us to the final and most resonant point from the sources: the future geologist's view.
If the Earth survives our current industrial age for another 50 million years, those future scientists, whatever they may be, will study the layer that corresponds to the 21st century. What are they going to see?
They will see a geological layer defined by an abrupt, multifaceted geological shift. The sources describe this future layer as containing unmistakable signs of human activity.
Our 13C shift is already well underway. The heavy metals are everywhere. Our synthetic materials are globally distributed and sinking to the bottom of the ocean. We are creating that robust, multi-layered fingerprint that a successful search for the Silurian hypothesis would require. We are the perfect analog.
It's a remarkable feedback loop and a slightly unsettling thought. We are simultaneously the detectives searching the past and the perpetrators creating the evidence for the future. And if the signature we leave behind is so clearly industrial, then finding a similar signature in the distant past would warrant intense, targeted investigation, even if the odds of preservation are so heavily stacked against it.
So, to briefly synthesize our deep dive, we know the definitive signatures that mark an industrial age: the isotopes of carbon, oxygen, and nitrogen, the heavy metals, the robust synthetics like plastics and PFAS, the radioactive markers, and the durable technofossils. We know the incredible challenges, that relentless mechanism of ocean recycling and continental erosion, and the extreme difficulty posed by natural lookalikes like the PTM that mimic our climate impact. And we know precisely where to look: deep ocean and ice cores, and specific terrestrial accumulation zones.
And we understand the ultimate significance of it all. This exercise is less about ancient reptiles and more about sharpening our perspective on our own fleeting but profoundly powerful geological moment.
It forces us to appreciate that everything we create, everything we use, will ultimately become part of the rock record, or it will be annihilated by it. We are making our own future fossil record right now as we speak.
That brings us to this profound philosophical takeaway from the source material. It forces us to face the idea that civilizations are ultimately fragile, and the vastness of time minimizes even our greatest achievements. The sources acknowledge the stark possibilities. Perhaps no civilization came before us. Perhaps we are the first to carve our mark so deeply.
And regardless of that, perhaps, the universal lesson still holds true. The Earth forgets easily. Everything becomes fragmented, blurred, or erased by the relentless march of geological processes. The most persistent thing we produce might not be our philosophical texts or our great art.
but our garbage and our pollution.
Sadly, yes.
What we leave behind, that thin layer of plastic, concrete, and unusual carbon, may be the only voice that speaks for us in the deep future. It tells the story of an intelligent species that harnessed immense energy for a brief geological moment.
And the thought we really want to leave you with, one that builds on this entire thought experiment, is this. If the Silurian hypothesis demonstrates just how incredibly hard it is to leave a durable mark, and if most of our current signature is based on environmental disruption and waste, what proactive, conscious actions might a truly forward-thinking civilization take to generate a durable, unambiguous sign of intelligence and foresight? What form of technological achievement, maybe deeply buried, chemically inert data storage, or vast engineered planetary structures, what would represent a proactive, permanent signature that proves intelligence without relying on environmental destruction? Something that ensures the Earth could not erase it in the next 50 million years. What is the geological definition of a lasting legacy?